Still just getting set up here. So yeah, welcome to the stream. This is mathpond. We're gone for a week, but now we're back. So yeah, we're getting into some complex analysis stuff. Man, this music is very distracting. Okay. Yeah, so we're getting into a basic introduction, getting a feel for complex analysis, mainly the study of holomorphic functions. So that's sort of where we started last time. That was the first lesson. So let's call this, I believe this is number 25. Hey Rex. So yeah, let's call this lesson 25. I think I just wrote complex analysis, but I guess more specifically I'll be talking about complex line integrals. I believe this is 25. So a quarter of a century here. Hey Fox Gamer, welcome to the stream, to the chat. Yeah, so we're gonna call this lesson a lesson on complex line integrals. And so maybe you've seen this. Maybe you've seen something similar in one variable calculus where one variable, I'll just kind of briefly sketch it, right? You have some function of one variable. Well, actually, I guess technically for line integrals, maybe you're working in like 2D, right? Actually, yeah, maybe I won't go too deep into that. But so you have these line integrals from one variable calculus, right? And it's basically just a generalization of your regular integral, except now you can sort of integrate over some path. If you have a two-dimensional function, like let's say we have a function defined on the plane. I guess I will go into it a little bit. So let's say it's some function fxy, function of x and y. There's a couple different notions in regular calculus about what it means to take. You can take, a couple different integrals. You can take like an integral of, vector valued functions along this line integral. There's different notions of integrals with scalar valued functions. So yeah, from single variable, two variable calculus, the stuff we're about to talk about is essentially a generalization, but it's a generalization with a very rigid structure to it, and that rigidity is basically what gives complex analysis its whole like flavor and like quote unquote like niceness, right? So yeah, let me just review quickly what we were introduced to last time. We were just talking about generally what is a function between complex numbers, right? And we said it was essentially just a two-dimensional map between these two-dimensional real spaces, right? So think of complex valued functions that are taking a domain. The domain is some subset of C, so usually it's some like open domain U. And we said a function here was essentially just two functions of two variables because the domain was two-dimensional and the output was two-dimensional. So it's essentially just two different functions and each one depends on these two different variables in terms of like real variables, right? So we said the function could be essentially written as like f of x plus iy was some u function of xy plus I times some v function of x and y. Okay, and this is essentially just restating what it means to be a complex function. It's just a function of two variables and the output is two-dimensional. So there's one dimension that's given by u and then plus I times another dimension is given by another function, which is this v here. Right. So is there any questions about that before I move on? So this is just basically a way of writing a function, right? We're saying that a function of this form is basically just two functions. And then we said we had a definition, which was that this function, if it was C1, which means that it's continuous and its derivative is continuous on all the points in U, if we view it as a real function, two real functions. So if f is C1, which we'll write as like usually f is in the set of C1 functions on U. And we define this special notion of this like, so I went back in the text and read about it. It's essentially just notation. So when we write df dz equals 0, or if it's identically 0 on all of the whole domain, all the points in U, then we called this type of function holomorphic. But again, we were a little bit, we were sort of a little bit hand wavy or naive about what the definition of this was. Since z wasn't a real variable, I guess it wasn't really fully defined what, you know, the partial f with respect to partial z even means. But there's a definition in the book which essentially just writes it as like a linear combination of the real partial derivatives. So yeah, if you look in the book and look at the definition of what this is basically just a placeholder. And the reason that we make this the definition, that if this is true and this is 0 for all the points, for all p in U, then the definition was that we called f a holomorphic function on U. Usually U is an open domain, or just some open set. So then we called this holomorphic. So then f is called holomorphic. Okay, that's just a definition. What's the importance of the definition? Well, it's essentially equivalent to these Cauchy-Riemann equations for each variable separately. Let me just lower the brightness on here. I can still read the chat though. So yeah, is there any questions about this? This is essentially what we went over last time, that we have a function between some open subset of C to C. This is like two real functions. We had a definition that it's holomorphic if the derivative with respect to z vanishes, or sorry, with respect to z bar. I'm already messing up here. If the derivative with respect to z bar is 0, and this was essentially like if and only if, or equivalent to the Cauchy-Riemann equations. So that was the first proposition, that if this holds, that's if and only if you have this relationship between the two partial derivatives of u and v. So basically the partial derivative of the first function with respect to x, there's some relationship between the partials of u and v. So yeah, is there any chat that I'm missing? I don't really know much about these, but I'm here because I'm curious. Yeah, well, that's good. Yeah, I mean, that's probably why most people are here. Okay. So yeah, holomorphic function, and the point of this definition was the Cauchy-Riemann equations. So this definition is set up to say essentially that the Cauchy-Riemann equations are satisfied. So that's the first proposition that we went over last time. So just to remind you, so if f is holomorphic on U, on the set U inside of C, then we have both the Cauchy-Riemann equations. So the partial derivative of the first variable with respect to x is the partial derivative of the second output variable with respect to the second variable y. And du dy is the negative of the other one. Okay. So Cauchy-Riemann equations, which essentially just says these, you have equality with both these partial derivatives. This is just equivalent to saying that the derivative of z bar vanishes on all of these points, on all of U. Yeah, I should say here also, for every point of U. So every p in U. This is true, that these Cauchy-Riemann equations hold, so the partial derivatives are equal. In particular, if we're assuming it's holomorphic, it's already C1, so we know these partial derivatives exist. It's just a matter of if they match up in this way. And if they do match up in this way, that's if and only if it's holomorphic. So it's essentially just equivalent to the z-bar definition from before. But yeah, I don't want to go too much in that. They could essentially just make this the definition, that it's holomorphic on U if and only if, these two are satisfied. I think the whole z-bar stuff is sort of unnecessarily convoluting the idea. I mean, essentially, if a function is holomorphic, it's just if and only if these two partial derivatives equations are satisfied. So you can forget about, derivative of z-bar if it's confusing, and it's essentially just, it's equivalent to this data anyway, so you don't really need to think about z-bar if it's, if you don't like it or it's confusing. For me, personally, it does get a little bit confusing because, you're taking the derivative with respect to a variable, but it's not a real variable. So, unless you just explicitly define what it means like they do in this book, then it's a little bit confusing. For sure, I think. Well, at least I'm confused by it, so. Even though I know what it's supposed to mean and I know what they're intending it to mean, but it's still confusing to me because essentially it's just equivalent to these two statements. So I don't know why they don't just make this the definition from the beginning. And I'm sure other books actually do that. So yeah, like I was mentioning last time, a lot of these complex books, they'll define holomorphic function as like one of 3 different things, and then they'll prove that it's actually the other 2 things. So like this book takes the definition to be essentially that the Cauchy-Riemann equations are satisfied, or that the derivative with respect to z-bar is 0. But we have other equivalent definitions, like, the original definition of a derivative, like the limit as h goes to 0 of f of a plus h, minus f of a over h. That's another definition, that limit existing for every point in U. Or you can talk about an analytic, a holomorphic function having a Taylor series, and that being the definition. Like a function is holomorphic on U if and only if around every point there's some convergent Taylor series. Right, but all of these things end up being equivalent, so you could actually take any one of them as being the definition, and then you can prove the other results. Hello, Jen. Oh yeah, which is the book? Good question. So yeah, I actually have it right here. So if anyone hasn't seen the book yet, this is a physical copy of it. So it's Function Theory of One Complex Variable, Green and Krantz. I think Rex might have posted a link, but quiet about that. So Megalomorph says, I've only seen the z-bar approach have any use when you want to use Stokes' theorem. Yeah, I mean, I don't want to say it has no use. I just find it confusing personally. I wouldn't say that it has no use. I mean, it's just another device to refer to these things, right? But it can be a little confusing if you're imagining it as some sort of like real derivative, but we've just now replaced z with an imaginary or complex variable. So yeah, I'm just going to sort of avoid it. I mean, essentially it's just set up so that these two equations hold anyways, so you could just sort of forget about the derivative with respect to z-bar if it's confusing, and the fact that it's 0 on all of U, that's just equivalent to this. So yes, yeah, Rex just posted the book. Thank you. Right, so that's what we did last time. Cauchy-Riemann equations. So now we're going to get into complex line integrals, which for complex functions are actually very interesting. So we'll see in a little bit that taking integrals, even in the real case, there's a cohomology connection to it. Not like a connection in that sense, but so when you're taking complex line integrals, depending on the topology of the domain or the manifold or whatever you're looking at it can actually change what the result should be. So a lot of integrals actually end up being 0 for a fundamental theorem of calculus reason, which I'll write in about a second. But so yeah, the point of my rambling here is to essentially tell you that we're taking these integrals like we would for normal calculus, but they're actually, a lot of the times they're giving us some sort of topological information, which is not so obvious. And there's a lot of these types of integrals in complex analysis where they're like, they have to be some integer multiple of some number. So for instance, like if you're using a numerical approximation, you might, you know what the respected result is supposed to be for some of these integrals is what I'm trying to say. But yeah. too much yapping, but let's get into the actual math of it. So yeah, we're doing complex line integrals. And there will be a fundamental theorem type thing if the function is holomorphic. So there's a sort of like fundamental theorem of calculus for complex line integrals. Okay, so this is a definition, just what does it mean to take a complex line integral? So if we specify some path, here it's going to be some function from an interval AB, like how you take an integral in regular calculus from, some number to some other number. But this is like some time in the path, you can think of it as. And we're getting as output complex numbers. So assume this is continuous. On AB. Yeah, continuous. Then the line integral from A to B of psi of t, this is just going to be defined to be the integral of the real part plus I times the integral of the imaginary part. So it's integral from A to B of the first part, which we'll call psi 1 of t dt, plus I times the integral of the imaginary part, which we'll call psi 2 dt. Okay, so this is just a definition. Which essentially just, if you really think about it long enough, this is just essentially saying two different integrals. So we're just taking the integral of the first function and the integral of the second function, and we're sort of viewing it as just two separate numbers where, this is the real component and this is the imaginary component. I'd love to understand the whole period thing. Yeah, we will definitely, you should somewhat understand that even by the end of this lecture even, I want to claim. From some of the line integrals we'll do as examples, I'll try to make that clear, what's going on. So yeah, this says if we have a complex function where the input is like some real interval, a to b, then we can define the integral of that complex function from a to b, dt. It's just basically the sum of the real part plus I times the integral of the imaginary part. So integral of the real part plus I times the integral of the imaginary part. And then another definition that if we want to take now an integral, instead of taking with respect to the real variable dt, we want to try to come up with a notion of what does it mean to take an integral of a complex valued function dz, where z is a complex variable. So this is actually a separate but related definition. So I'll write a big line here so you know that these are different. But now we're going to be defining what does it mean to take an integral over a path gamma of a complex function, which I'll write capital F of z, dz. And the definition says if I want to know what's the integral over a path gamma, I just need to parameterize gamma by some curve, and then I can do some sort of like chain rule type trick, and the definition is essentially, well, it's not really chain rule. We're basically defining it as if the chain rule should work. But basically, we're just going to parameterize the curve gamma from a to b, and then we're just going to take an integral from a to b of f, and then z is going to be parameterized by gamma, so it's really f of gamma of t. And then instead of dz, z is going to depend on gamma. So you get some sort of chain rule type thing, and you're going to get the derivative of gamma with respect to t times dt. So it'll be d gamma dt, and then times dt. Hopefully you can read that. So capital F of gamma of t times the derivative of gamma with respect to t, and then all of that times dt. And then we're going to take that integral. And of course, you need to check some things like, does this depend on how we parameterized gamma? Of course, it doesn't because of this chain rule stuff going on. So this is a definition for any parameterization of gamma. For any C1 parametrization, or maybe it could even be C0, I'm not sure. Oh no, it has to be C1 because we're taking a derivative here. So for any C1 parametrization of gamma. So what is this saying? It just means if I have a path, so we'll do an example in a second, but let's say I have a path that's like a closed curve that goes like around the unit circle, for instance. So for instance, like this one has a parameterization where I go from 0 to 2 pi, and I plug in like e to the z, or e to the theta I, right? Theta goes from 0 to 2 pi. So that will parameterize this whole circle once. So that would be like our gamma, and then I can integrate a complex function around this curve, just like how I would integrate a real function along some curve, except now we have more structure here, because we have, not only do we have two output variables, right? So now it's like integrating two different functions, but also we have a multiplication structure that's also getting integrated, right? Because this is f of z times dz. So f of z is a complex number, and dz, which is basically d gamma dt times dt, that is a complex number as well. So we're multiplying two complex numbers together. So it's sort of like an integral, but there's like a little bit extra stuff going on, right? Okay, yeah. So we'll talk about yeah. Let me just state this fundamental theorem of calculus. So now we have an integral over a path. If the function that we're integrating has an antiderivative, just like in the one variable calculus, then we can basically just look at the endpoints of gamma and take a difference, just like in one variable calculus. Okay, so any questions before I erase all of this? So basically we're just defining, if I have a path in C, what, giving me complex numbers, what does it mean to take an integral from the start of the path to the end of the path, dt. And then if I have a complex valued function and I have some parameterization of a path, then this allows me to integrate over that path as a complex function times dz. So I'm getting a complex number times a complex number, and this is some notion of like an aggregation of all of those products. All right, I don't think I see any questions. But yeah, the idea is very similar to for one variable calculus, where remember for one variable, I think Zach was talking about a while back, you can think of the integral as like the signed area under the graph, where you're accumulating area, whether it's positive or negative, as you go over some interval of the function. This is very similar, except now you have more dimensions, so the way you can integrate over paths has basically increased. Now we can integrate over any basically differentiable path as long as we have some C1 parameterization of it. And this is saying that it doesn't matter how you parameterize it, as long as you have some parameterization, we can make this definition, it's well defined, and we can define this complex integral this way, which then essentially just becomes a complex real integral, right? Because once you take this product, you just have a complex number, and then it's just dt, so you're back to this original definition. So once you fix a parameterization, then you just use the first definition. But before a parameterization is fixed, you can sort of think of this object as like an abstract idea that it's maybe, it's abstract in the sense that it doesn't depend on which parameterization you pick. You can pick a different one, and there's some sort of like renormalization thing happening, not like in the physics sense, but you could just parameterize this curve at different rates of speed, right? So you want to, this term is basically readjusting for the fact that you could be parameterizing this curve at a higher constant rate, or maybe the rate isn't even constant, right? There's a lot of different ways to change this C1 map. In fact, I think you can I was thinking about this before I started teaching the lecture today. I think you can possibly compose with like any automorphism at the beginning, right? Any C1 automorphism of whatever your domain is, like A to B, right? So you could, any self map from A to B to itself that's C1, you could compose with that at the beginning as long as it's invertible. And then you get a new parameterization, but then you're going to get a new, a new chain rule term. This d gamma dt might change, right? So yeah. Anything I'm missing? I think I basically covered everything here. So yeah, that just defines our complex line integrals, and then now we can sort of play around with that definition and see what we get for some specific examples. Let me get my hydration going real quick. I'm trying to get better at streaming, like a little more relaxed and kind of like not so serious all the time, I guess. I know I'm not like super serious to begin with, but right, so the last thing I want to say about these line integrals in terms of theory before we jump into the actual like calculations is this fundamental theorem of calculus. Which, if you haven't seen this stuff before, you can really think of this as like a special case of this Stokes' theorem, which essentially is like your true fundamental theorem of calculus for any dimension and any type of these like different incarnations of differential forms. Thanks, Rex. So yeah, you could think of this as a fundamental theorem for this specific case, but it's essentially like a shadow of this, Stokes theorem type idea. Which is just saying, so now in this case for holomorphic functions, so let U be a domain, be an open domain again in complex numbers. So be open. And again, we have some closed curve gamma. Defined on A to B to U. So we're parametrizing some path in the open set U, where now some other function is defined f. Let's assume gamma is C1. C1 curve. So again, that just means it has a derivative, and the derivative is continuous. So if f is a holomorphic function, the statement is, so if f is holomorphic on U, then this integral, so then the difference of f of gamma of b and f of gamma of a, so saying the difference of the value of the function at the end of the curve at gamma of b minus the value of the function at the beginning of the curve at gamma of a is, and then it's, if it's going to be similar to the one variable case, it needs to be equal to some integral, and it's going to be equal to the integral of the derivative. So it's equal to the integral from a to b, or actually we can just write it as on gamma. So it's equal to a complex line integral over this path gamma of the derivative. So df dz, which is just the complex integral if it's holomorphic, dz. So essentially it's the same theorem as the one variable case, just in the one variable case you don't have functions into C, you just have functions from some open set in R into R, right? And then your line integrals for the real cases, you're always just taking integrals over the real x-axis. So you never really need a parametrization. Yeah, and then so you can see this is just essentially the same statement as the one variable case, except now we've upgraded our notion of the different types of lines we can take integrals over. But other than that, it's essentially the same idea. So it says, if our function has an antiderivative, which you need to be careful because not every function does have a complex antiderivative, but this statement is saying if it does, then the integral of that derivative is just equal to the value of the difference of the function at the two endpoints. So f at the endpoint minus f at the starting point is equal to this complex integral. And just be careful that you remember there's a complex integral, so it's respect to dz here. You don't have a dt here. So yeah, this is truly, you're taking it. Somehow you can think of this as like Riemann sums, but now your rectangles are like complex rectangles, if you want to think of it like that. But yeah, this is saying in that limit, if you take all the limit over all those Riemann sums, right, then you should just get this difference in the end, if it's holomorphic. So it's very important you need f to be holomorphic. If f is not holomorphic, then this is not necessarily true. Okay. Any questions about that? So yeah, this is basically the last theoretical thing at least that I'm gonna like state formally. And now we'll just do a few examples of actually calculating these line integrals for certain functions. Yeah, pretty much all holomorphic functions. But you'll notice that depending on the domain that the holomorphic function is defined on, you actually may get different results with these integrals. So you have to be very, very careful. And there's like very high, theoretical ideas going on here behind the scenes. I just want to make that clear. But yeah, just calculating these integrals is pretty simple usually, especially if they're simple like the examples I'm about to go over. But right. Right, so let's just go over a few actual integrals. So essentially we'll be figuring out some parameterization like this of u, some set that we have some holomorphic function defined on, or maybe it's not holomorphic, just some function. And we'll calculate some of these line integrals. Okay, so just some examples, but these are actually very important examples. So I didn't pick these like arbitrarily. I didn't just pick some random complex function and then show you how to take the integral of it. So the integrals of this have some sort of topological meaning. There's a whole story behind this basically. So integrals of functions into C. So first example, we'll start off really, really easy. So f of z is equal to z. This is the function. I said we don't really use differential with respect to z very often, but sometimes it is useful to just check that, because the function doesn't depend on z bar, that this is actually zero identically everywhere. And, it has a holomorphic derivative. The derivative is just the function, just 1, right? So yeah, since this function has and the antiderivative is also a function capital F of z, which is z squared over 2, right? So this function is actually defined for every number, this function right here. It's defined for every complex number. Like I can plug in any complex number here I want, I get an output. Here it's just the identity map, so it's kind of boring. But that map actually has a complex antiderivative, which means it has a function whose derivative is little f, but and obviously it has a regular derivative because it's holomorphic, which is just 1. So in this case, because it has an antiderivative, capital F of z, there's actually no need to even compute the integrals. So if we wanted to know, if we wanted to compute like what's the closed line integral around the boundary of, say, like the unit disk, so you'd write that like this. So that would be this path I was showing you before. And now our function is just z dz. Well, because this function is holomorphic on the entire interior of this set, and this antiderivative exists for every point in the domain, we can just use the fundamental theorem of calculus and conclude that this is just the value of the antiderivative at the endpoint minus the beginning point. But if we're taking an integral around the boundary of the disk and we're starting and ending at the same point, this is just, z squared over 2. I plug in the endpoint, which is 1, at 1 minus z squared over 2. And I plug in the same endpoint, which is the beginning point, 1. So it's just 1 over 2 minus 1 over 2. So this integral, by the fundamental theorem of calculus, should just be 0 because there's an antiderivative. Z squared over 2 is the antiderivative, and the integral is starting and ending at the same point. So if I subtract off the two values at the endpoints, well, the points are the same. So I just get the value of the function at 1 minus itself. So I get 0. All right, so any questions about this? So yeah, we didn't really do any computing yet, but if we did do I guess we could even just plug in the numbers and show that we get 0. I guess I could do that real quick. Yeah, that seems fun. So yeah, fundamental theorem of calculus says that this should be 0. And then let's actually just plug in by the definition what that is, and we'll just show that it's 0 explicitly. Okay, so our function is just z. Our curve is gamma, so we can parameterize the unit circle, the boundary from 0 to 2 pi. To c, this is just the function that sends t to e to the it. Okay, so we have an integral from 0 to 2 pi of the function z, which we've now parameterized as e to the it. And then I need to multiply by the derivative of that. So this is I e to the it, assuming that the derivative rules all work the way that we would expect that they do, but they do. So we have chain rule for complex numbers. So yeah, derivative of e to the it is just I e to the it. So that's just chain rule, or power, yeah, chain rule. Yeah, and then dt. Okay, so what is this? I can pull the I out, right? So it's just I times this. E to the it times e to the it is e to the 2it, right? Yeah. Oh no, wait, yeah. Okay. And then what is the integral of 2 to the it from 0 to 2 pi? Well, this is really just two integrals, right? So it's integral from 0 to 2 pi of the real part, so cosine of t, or cosine of 2t, I guess. dt plus I times the integral from 0 to 2 pi of sine of 2t. dt? Okay. And then, so yeah, what's the calculus relation we need to show that these integrals give us 0? So essentially the real and the complex integral should both be 0, or else we have a problem here. But I think there's like, what's the double angle formula? Here, we'll show one of them as 0, and you could just take my word for the other one. Which one's the easiest one? I think cosine of 2t, what's the relation again? This is like 1 1 minus cosine t. No, I'm mixing these up. Oh, double angle formula, right. Okay, so this is like sine cosine? 2 sine cosine? Maybe somebody can help me. Is there some intuitive reason why this one should be 0? Well, sine of 2t, we know that one's even, so... Oh, wait, no. One of them is symmetric around pi, is an odd function around pi, I think. So one of them is like clearly 0. And then the other one, I think all the positive part cancels out with all the negative part, or... Yeah, something like that. Who has, you can just notice that the positive area of cosine and sine are the same over one period. Right, that's a good intuitive way to think of it, I think. Sure. Yeah, like sine and cosine are basically equal to each other, just shifted, right? So, and they're equal up to a 2 pi period. Yeah, proof by period. No, yeah, that's definitely the intuition. Like cosine and sine are traveling over the same values essentially over a full period from 0 to 2 pi, even from 0 to pi. Right. I know there's some cosine of 2 pi. What is this, like 2 cosine t sine t or something? I forget all these relations. I didn't write any of this down. So you could probably use that and then like product rule or something. But yeah, you want to show that each one of these integrals is 0, basically. Those are U substitutions. Oh, okay. Oh, right. Oh, sure. Right, yeah, you could just use substitute. I don't know what I was thinking. Right. Just use substitution. Okay, yeah, so I'll leave that for the reader. I don't want to waste the board space. But yeah, just use substitute for 2t. So it'll be cosine of, u du over 2 or something. And then you just get like, yeah, antiderivative is like sine u over 2. Yeah. Yeah, and then the antiderivative is cosine, and then cosine's value at 2 pi and at 0 is the same. So, yeah. Okay, so yeah, essentially you can show both these integrals are 0, so you get 0 plus, 0 plus I times 0, right, which is just 0. E to the z has complex antiderivative. I feel like we can use that, or we can use, yeah, that was the first thing I was saying, yeah. So if we just refer to the fundamental theorem of calculus, we say, okay, there's an antiderivative for our function, which was z. The antiderivative is z squared over 2. And then we can use the fundamental theorem of calculus to say, because we're integrating over a closed domain, the endpoint and the beginning point are the same, so the integral must be 0. Or you could just check by hand. You have to actually compute that these two integrals are 0. But yeah, either way you think of it, it's, same result. The integral should be 0. So, yeah, u sub 2t. Okay, so that one is 0. And now we'll do a very similar integral, but instead of integrating the function f of z equals z, we'll be doing f of z is 1, the reciprocal, so 1 divided by z. Okay, so second example, take a complex line integral. Our function is 1 over z, like this. And again, we're going to integrate it on the boundary of this closed disk of radius 1. Right, so what is the parametrization? I already wrote this before, but so y of t is e to the it, and t is between 0 and this 2 pi. Yeah, so the one thing I want to point out is what's different about this function and the first function we just integrated, f of z equals z. So what's the main difference between these two functions? let you think about that for 10, 15 seconds. So we did f of z equals z, and now we're looking at f of z is 1 over z. So what is the main difference between these two functions? So Megalomorph says the antiderivative in z isn't a single valued function, which means, yeah, it's not a function at all, right? So it doesn't exist, right? Yeah, that's true. Why doesn't it exist? So it's not analytic there. Well, it's analytic everywhere it's defined. It's not analytic on every point in the interior, that's true. But everywhere it's defined, it is analytic. So, I mean, clearly there's a point where it's not defined, right? That's clearly different than the case for the first case, right? F of z was defined for every point. But clearly there's a point that we can't define this function, and that's at 0. And in fact, there's no way to like fill in that hole, because every point that we plug in that's near 0, the values of the functions are increasing without any bound in absolute value. So it's not even like we could fill in the missing value at 0 and say, oh, well, maybe the function's value is actually just 0. It's getting closer to 0, but it's just not defined there, right? That's not the case here. The function's actually blowing up at 0, and there's no way to fill in that hole and get a full function. So there's a main fundamental, I want to stress, difference between these two functions. And yes, as Megalomorph says there's no antiderivative of this function on the domain, and that's important because it isn't defined on the full domain. And we'll show, or I'll explain later, that if you do have a function that's defined on a simply connected domain, then the antiderivative does always exist. So the fact that this function doesn't exist on a simply connected domain, and that's the main difference here, at least if you include, points near 0. Right, so here we have a function, it's defined everywhere except at 0. So there's this like hole in the definition, and this actually tells you the fact that this function exists here, and we're about to show that the integral around the circle is not 0. That's actually telling you something about this hole, that there's a hole in the topology of the space that the function is defined on. So yeah, the antiderivative log of z isn't defined because either z isn't 1-to-1 on c. Yep, that's true. That wasn't in z, it was ln of z. Oh, I see what you're saying. Okay. Right. Not lowercase ln, it was capital Ln, right. Sure. But I don't like the word multi-valued function anyways, because a function by definition can't be multi-valued. That's like the first thing we teach all of our students. So I hate the fact that they use the word multi-valued function and they look at their students with a straight face, even though they, constantly pressed on them the first year that, what do we say in calculus? It's a function if it passes the vertical line test, which means it only has one value as the output, right? If it has more than one value, it's not a function. So that's just by definition. But I wish they would prefer to use like terminology like, I don't know, just multi-value, anything other than multi-valued function, honestly. Right, so let's compute this. So we're taking the line integral. We're starting here at the point 1. We're traveling e to the I t around from, t varies along this coordinate. We're going to start and end at this same point. And we're going to take the integral. It's very similar to the last calculation, except now we're going to be plugging in a different function here. Same parameterization though. So yeah, by definition, this becomes an integral from 0 to 2 pi of our function. So 1 over, now we're going to plug in e to the it. And then I'm going to multiply again by the derivative of the parameterization times dt. So it'll be times I e to the it dt. So that's like our chain rule part, right? Multi-valued function, oh, sorry, yes. Jen says it's just a function into the set of subsets of C. Is that true? Is that true? I guess you could have multiple copies of C, is that what you're saying? And you're just splitting the function. So some copies go into the first copy of C, some values go into the second copy of C. Yeah, you could probably say something like that. And in fact, most multi-valued functions actually show up naturally as like the zero set of some complex polynomial in higher dimensions. So usually you are, sort of doing like something like that anyways. Multi-valued function in complex analysis is shorthand for a relation that corresponds to a ramified cover, I guess. Yeah, of course. I know that these things exist. I just don't like the terminology. I just think function, by definition, is single valued. To say multi-valued function to me is basically like a contradiction. That's literally the only thing we want from a function. It's like a relation that has a single output for every input, right? So I just think multi-valued is just terrible terminology. But of course, I understand what the idea is. Yeah. Okay, yeah, so we have 1 over the parameterization. So this is 1 over z, except now z is this only taking on these values, where t is from 0 to 2 pi. Multiply by the derivative of the parameterization times dt. You can see that the e to the it cancels with the e to the it here. We basically just have an integral from 0 to 2 pi of I, which is a constant function, so I can pull it out. And so it's just basically dt from 0 to 2 pi. The antiderivative is t. So I can plug in 2 pi and then plug in 0, take the difference. So I just get 2 pi times this I. And earlier in the lecture, I was saying that when you take these types of integrals, you're only going to get integer multiples of this, and that's the case here too. So right, I'm not sure what I was trying to add to that, but yeah. So the main important part here to take away is that the integral is not 0. That's the most important part. So we took the integral and we got something non-zero. And this seems to, at first glance, it seems to contradict the fundamental theorem of calculus, because it seems like we took an integral along a closed path. We should be able to just apply the fundamental theorem of calculus and say, all right, I'll just look at the antiderivative and take the difference of the values of the function at the antiderivative at the two endpoints. But because the endpoints are the same, like the last problem, it should just be some number minus itself, right? But the main problem here is that this function we're dealing with here does not have an antiderivative on the domain where it's defined. And so when you try to apply the fundamental theorem of calculus, the first thing you need to do is find an antiderivative and then plug in the two endpoints and take the difference. But it turns out in this case, if this was going to have an antiderivative, it would be some sort of like this, complex log type thing. But you find out you actually need to restrict the domain for this log to actually even make sense. So if you try to define a quote unquote like complex log for every single point here, and you don't include any sort of branch cut or anything, you'll find that there's no way to do it without, there's just no way to do it. There always has to be some sort of discontinuity at some point. And so basically, the only way to find an antiderivative of 1 over z is to restrict the domain so that it actually is simply connected. But yeah, the interior of this is not simply connected because the function's not defined at 0. So basically, you have a hole where it's not defined. So that means we can't apply the fundamental theorem of calculus. And in this case, which is actually a very surprising result, you take a closed integral around a path, you start and end at the same point, but your integral is not 0, even though your function was holomorphic. But it didn't have an antiderivative. So that's the key difference that a lot of people will probably mess up or confuse in their head. Just because this function is holomorphic itself doesn't necessarily mean it has an antiderivative, except if you're on a simply connected domain, then it is true. But because this function is defined on the interior of this disk but not at 0, then it's actually defined at every point except for 0, which is not a simply connected domain anymore. So yeah, I think it's a surprising result. It tells you some sort of topological information about the domain that you're integrating over, even though there's sort of a priori no topological information even going into the problem. We're just looking at some holomorphic function. The only topological information is where is this holomorphic function defined on? So what is the shape of the space that this function is defined on? And it's, it's not a simply connected space. So that's and in fact, there's no way to extend it to be defined on a simply connected domain because of what I was saying before, that as you get closer to 0, this function blows up and there's no way to continue the discontinuous point and make it continuous. Except you don't run into this problem if you integrate 1 over z squared. Yeah, that's a great point, but the 1 over z squared has an antiderivative. So that's the main difference, yeah. And that's why I chose this particular function. Yeah, so if we did the same process, we try to integrate 1 over z squared, you'll actually find that the integral in that case actually is 0, because that function does have an antiderivative. And what's actually really, really cool is I want to say this, but without looking at, I believe this is true, so take this with 90% confidence, but this is like the span of this one function is actually all possible functions that have non-zero derivative on this when you do this. As long as it's, defined at, there's probably a bunch of stipulations I need to put in there. That's why I'm being cautious. But if you look at any function that's defined on the unit disk except at 0, then it has some Laurent series. And the only part that has a problem in the Laurent series is the 1 over z part. The integral of every other part of the Laurent series has integral 0. So in some sense, like the 1 over z part is like the only obstruction to the integral being 0. If you have any other function that's defined on the disk except possibly not at 0, the integral will be 0 unless it contains some 1 over z part. Then it won't be 0. So it's kind of cool. It's in some sense it's like the only part where this, integral being 0 thing messes up is specifically for this type of function or some scalar multiple of this function, of course. We'll have the same problem. Okay, so any questions about that? So we integrated a holomorphic function that had a holomorphic antiderivative around the disk. We found that the integral was 0 because the existence of an antiderivative meant that it was that we could apply the fundamental theorem of calculus. Then we looked at a function that was also holomorphic on the inside of the disk, except it wasn't defined at 0. And this particular function had no antiderivative on the interior of the disk. And so it turned out that just by a hand calculation, by parametrizing the circle, we just calculated by hand that the integral was 2 pi I, which is not 0. So that's a big result here, and that's specifically because this function has no antiderivative on this non-simply connected domain. The fact that it has a hole at 0 where it's not defined changes the topology and thus allows, because the topology is not your trivial topology, it allows some sort of non-trivial integral here. So there's a direct link between the integral value being non-zero and the homology and cohomology of the space that you're integrating over. So it's a very interesting relationship between topology and complex analysis. Okay, so do we have any more of these? Yeah, I basically just went over this. So no, 1 over z has no holomorphic antiderivative on c minus 0. Yeah, so let's just look at this one more way. Something integration is a homomorphism from the fundamental group of the domain. I don't think it has to do with the fundamental group, but I believe it has something to do with the cohomology classes. Like there's, if you look in de Rham cohomology, there's some sort of pairing, I believe, that it has to do with integrating the forms. And this is I'm probably saying a bunch of stuff that's incorrect, but there's a direct connection between integrating holomorphic forms on the manifold and certain cohomology classes. And the fact that this integral is not 0 means that this is somehow representing some non-trivial cohomology class in the domain where you take out 0 from the complex plane. But yeah, I'm not so sure about the fundamental group. Maybe there is a fundamental group homomorphism. I'm not, maybe someone else in the chat, if they are reading that, they can chime in, but I'm not so sure. But yeah, I know that the DRAM, or maybe it doesn't even need to be DRAM complex itself, but the differential forms, the integration becomes some sort of pairing and gives you, yeah, I'm probably just totally butchering this, but so yeah, we're not getting into too much into that, but yeah, you could of course look up more about that in your own time if you're interested. So what is the problem with this domain, the fact that this function is not defined at 0? And the reason is that if I want to define the antiderivative, it seems like the right notion from our normal calculus would to just be to pick a point. So maybe I'll call this point z near z naught, just some point in the domain. And if I want to define what's the value of the antiderivative at z, I can usually just define a path between the 2 points and take the integral of the function from z naught to z. And that will usually be, quote unquote, an antiderivative. But unless the set is that you're integrating over is simply connected, there's actually a problem with this definition. So let's call this gamma 1, and let's say we possibly could integrate it along a different path, and we'll call this gamma 2. So we would like the antiderivative to just be defined as the integral. This is like in normal calculus where you pick some point and you take the integral from that point to some other point. Right, we're just starting at z naught. I'll call this like, let me call this w just because I'm going to use d0. I'm going to use dz. So capital F of w is an integral from z naught to w of, in this case, it's 1 over z dz. And this is just any curve from z naught to w. But the main problem here with doing this is that it actually depends, if the curve is not simply connected, the value that you get in the end actually depends on which curve you pick. And it actually depends on the homotopy class of the curve. So really, if I pick any curve that's similar to gamma 1 but maybe slightly deformed, I'll get the same value as the integral over gamma 1, but I'll still get a different value than the integral over gamma 2, and this has its own cohomology or homotopy class of paths where, so any curve that's homotopic to the first path, I'll get some answer, and any curve that's homotopic to the second path, I'll get a different answer. And the reason that the closed integral is not 0 is because these are different. Because if these were always the same, then I could just take one and then take the minus of the other, and I would always get 0. So the key fact here is that I'll put this in big letters. So if f has no, if the domain U is not simply connected, is not simply connected, then I'll put it in quotes for now, a unique antiderivative need not exist. Okay, and it needs not exist, at least uniquely, because of this exact problem, where if I want to be able to define it as the integral over any path from one point to the other point, but if it depends on the homotopy class of the curve of the path, then it's not unique. If I go along one homotopy class of paths, I get one answer, and if I go along a different path, then I get a different answer. So the only way that we can do this uniquely is if every path can be deformed to every other path. But the problem with our domain here is that there's a hole here. So any path over here, there's no way to deform it to be gamma 2 without, at some point like breaking the link and like bringing it around the hole, right? There's no continuous path to get this path over the hole without, somehow breaking the line. Because at some point you'd have to cross the point, but the point is not in the domain, right? Because of the homotopy invariance, relative endpoints of path integrals of holomorphic functions, integration is naturally a map from the right. That's exactly what I was just saying. Yeah, from the fundamental group to C, which sends concatenation of paths to sums. Right. Restricting to just loops, we get that this is a homomorphism from pi1 of U, right, with the base point to C plus. Oh, okay, right. And then the homomorphism is just given by integration, right? Is that what you're saying? I think that's what you said. Yeah, integration. Yeah. Okay. Right. So yeah, basically that's just the person in chat. Megalomorph is essentially just translating what I was just talking about here with this picture into different language. So if you have a simply connected domain where there's no hole missing, then I can just pick any base point z naught. And if I want to know what's the antiderivative at some other point w here, then it actually does make sense to just take any path from z naught to w and take the integral of f of z dz. And that will give us some, capital F of w, some antiderivative. But this definition only makes sense if the domain is simply connected, because then any path this way can be deformed to any other path. And I know that the integral is basically constant along any homotopic path. So that would just mean since any curve could be deformed to any other curve, then the value of the integral is the same no matter which curve I integrate over. And that means that our antiderivative is well defined. Of course, we can take a non-simply connected domain and do this process by just restricting the domain to some simply connected subset of it. And that's essentially what you do for the complex logarithm. You take a branch cut, then your domain is simply connected, and then you can define the complex logarithm uniquely in that case. But of course, it depends on where that branch cut is. Depending on where the branch cut is, of course, you're getting different functions, because, for one, the functions aren't even defined on the same domain, right? So yeah, if your function is not simply connected, like in this case, I can throw out the hole, and then I can make a branch cut to the boundary, and then if I throw out this line, then the rest of the set actually is simply connected, and then I can just travel around that set, and there's a unique homotopy path for every curve if you throw out this line here. If you don't throw out the line, then it's still like a donut type shape, and you still have a hole in it. So you still have this topological thing missing from the homology group, from the first homotopy group, first homology group. I think that's fleshed out version of what Gen X168 means. Yeah. Oh, something. Oh, right. Sorry. Yeah, I didn't see that was Jen's comment. Right. Yeah, I get it. Sorry. Yeah. Thanks, guys. Thanks for keeping me paying attention. Okay. Do I have anything else here? Yeah, so that's basically the final result I wanted to go over, which is that there's this topological connection with integration here, that if the function is simply, if it's defined on a simply connected domain, then there always exists an antiderivative, and then you can always use the fundamental theorem of calculus to say that any closed integral on the simply connected set will have integral 0. But, of course, if your situation is different and you're not defined on a simply connected domain, if there's a hole in the set of definition, like for 1 over z, then if the function doesn't have an antiderivative, which there's no reason it has to if the domain is not simply connected, then you can get these integrals that are non-zero, like the 1 over z one we just did before. Okay. So yeah, this is some of the nicest quote unquote math that I think mathematicians get to study, because one, it's fun, you're doing like calculus, like integral type stuff, but then there's this topological component, which is like a very deep aspect of mathematics where you're getting these non-zero calculations for these integrals, and you're actually it's yielding you topological information about the domain in which the function is defined, which I think is very cool to be able to get. This is a big theme in math, where you have the connection between some sort of algebraic structure or some sort of topology, and they sort of play off each other, right? Algebra versus topology. In this case, it's like complex analysis, which is calculus and real numbers, and it's telling you something about the topology of the shapes, which you sort of think of as some notion that's, beyond calculus, right? You don't need real numbers necessarily to talk about topology, right? It's just sort of abstract notion of shapes, and there's no sort of analysis or complex analysis stuff built into it. So it's kind of interesting that there's this connection between integration and topology here. And when you have the residue theorem, you get that contour integrals can be calculated just by looking at the function at a finite number of points, which is just wild. Yeah, I agree. Yeah, I mean, here you essentially, once you know more theory, we could actually just say any closed curve around this point has the same integral, right? Because they're all homotopic to each other. So yeah, there's a lot of deep topology stuff going on here with these integrals. So when we take these complex line integrals, it seems like we're just doing some sort of like procedural thing to compute these things, but I really wanted to point out the topology connection and the fact that these integrals being zero or non-zero actually has this topological component to it that's not, very, very far from obvious, especially for newer students. So yeah, I think that's it for now. Oh, we're like 10 minutes over. So yeah, I'll hang out for a little like I normally do, and I'll take any questions you guys have. But yeah, that's pretty much all I prepared for today. So I hope you enjoyed that lesson. This has been mathpond. I'll be here tomorrow, Wednesday, for maybe an hour or two. We'll go over some examples. You can post in the Discord if you want any specific questions to be done out on the board tomorrow. And then Friday, we'll get into some really interesting stuff. So then all the complex stuff is gonna really turn up on Friday. We'll start getting into like Cauchy's integral formula, theorem type stuff. And then probably not by Friday, but we'll eventually be getting into like this Louisville theorem, which you can prove using Cauchy's formula. And then eventually you can prove the fundamental theorem of algebra with that. So very deep connections here. It's basically, the intersection between analysis, fundamental theorem of algebra, and also this topological story component that's going on as well. So very, very deep connections in complex analysis. And I've never found a mathematician that didn't even say complex analysis was like at the top of their, favorite subjects. Even people that didn't even really study analysis much, they also like complex analysis because there's a very rigid algebra component to it as well that people tend to like, even though it is fundamentally like a study of like analysis. And when you have residue theorem, yeah, I already read that, right? Yeah. Yeah, no problem, Jen. Thank you for showing up. So I think I'll just end it here. Any questions, please put them in the chat. I appreciate you guys showing up, and yeah. All right, I'll just end it here. Stop recording.